I'm going to talk about counterintuitive yet efficient regimes for MBQC. This was joint work done by me with Wang Yang and Robert during when we were at UBC, but yeah, now we are at LUH. And this is based on the work here, so from this PRL. So first I'm just going to tell you what the result is, and then I'm going to explain how we get there. So we consider symmetric ground states. The fact that their ground state is not so important, so they just need to be symmetric, picked from a quantum phase. That's my description of a quantum phase. These are some qubits in a phase, and then we unlock the computational power of those phases using local measurements. And this line of work provides resource optimal measurement pattern. So what is the most optimal way to do the measurement so that you can get a particular computation. This result has to do with correlation. So these two regimes I'm going to talk about. So imagine this is your set of qubits, and then so I've drawn the qubits now this way. The green ones, that's where you perform the algorithmically useful measurements. So these are the measurements that give you some non-trivial computation. And so in this regime they are far apart, and that's what I call uncorrelated. This is relatively easy to analyze, but it turns out it's efficient in a certain way. I'm going to tell you how it's inefficient, and yeah, you can find a lot of examples of this regime in these papers here. And the regime I'm going to talk about is this strongly correlated regime where these measurements are very close to each other, so it becomes very hard to analyze, but it's optimal in this regime in a certain sense. I need to define what I mean by efficiency, what it means to be inefficient or efficient, but that's kind of the high level result. So here is the outline of the talk. This is in the context of MBQC, so I'm going to talk a little bit about what is MBQC, although maybe for this audience it's not so relevant. And then I'm going to talk about this concept of a computational phase of matter. This was mentioned by David in his talk also, and Paul is also going to talk a little bit about that. I'm going to give some motivation of looking into these phases, and then a short history of the question, and then I'm going to talk about the thing we added to this formalism, and then some outlook. Let's start with MBQC. So this is one of Robert's typical slides. You have two kinds of measurements in MBQC, not MBQC, in quantum mechanics. You have unitary dynamics, so it's rotations on a Bloch sphere, let's say, and it's deterministic. And on the other hand, you have projective measurement type evolution, so this is random. But from the context of computation, they're equivalent. So you can if you build your computational model based on this, you get the circuit model. If you base it on this, you get the MBQC model. Okay, if you build it on measurements, this is the scheme you get. This is the typical cluster state picture. So you start with a highly entangled state, and then you perform local measurements on it, and the information is written onto the resource state, processed, and read out all by adaptive single qubit measurements. The interesting thing is that universal resource states in this context exist, in the sense that by this process you can simulate all of quantum mechanics, and those kinds of states are, for example, cluster state and AKLT states and so on. Why are we looking at this concept of computational phase of matter? These two motivations I give. One is asking how rare are MBQC resources. So it turns out any scheme of MBQC, the computational power depends mostly on the initial state you start with. So the question is, how rare are these MBQC resources, in the sense, if you start with some random states in Hilbert space, how much computation can you generate from them? And so this is the night sky, for example. So here I want to ask, for example, if I look at resource states in like a huge Hilbert space, do they form like continuous lines, or are they like individual stars, for example. So individual stars in this picture will be the cluster state and the equality state. These are individual points. I want to ask, can we actually form like some Milky Way or something like this, some continuous structure in the Hilbert space in the context of MBQC? There's one general result that is known in this context. So this is actually surprising. If you pick out random states from the Hilbert space, it turns out that only the tiniest fraction of states, which is, well, this fraction exponential of minus n squared, they can be useful for any MBQC at all. So all the other MBQC that you can do on all the other states, they're just trivial. And the reason is also interesting. The reason is that all the other states in the Hilbert space are actually too entangled to be useful. But now you can now change the question a little bit. You can maybe ask, okay, what if I add symmetry to this equation? So if I look into some symmetric subspace or symmetric states, does this picture change? Okay, so specifically you look at add some symmetry to your system. You look at zero temperature phases and then a spin lattice of qubits, and then you have a bunch of phases. So these are supposed to signify different kind of phases, and this is some phase boundary. And it turns out that in this context it does. So with the computational power of MBQC, so the MBQC power of these states here, they are uniform across phases. So any computation you can do here, you can do it here, here, effectively everywhere. It can only change when you cross this phase boundary. And the other motivation we have is, can we classify MBQC schemes by symmetry? This is more of a particle physics kind of idea, like as you can classify all elementary particles by some symmetry, classification of symmetry, maybe the same thing can be done with MBQC. Okay, this is probably David's favorite picture about the meat grinder. So this is some symmetry of a Hamiltonian or some phase put in, and then from there through an algorithm you get a MBQC scheme out, and then the question is, can we do this for all MBQC schemes? So this is some symmetry or some physics put in, and then you get some computation. So I'll give you a little bit of an overview of the previous results in this context. I start with Miyake. So this was a work done almost 15 years ago, and this is kind of the start of this field of research. So let me talk a little bit about what this is. So Miyake considered a scheme of computation which is hybrid. It's half MBQC, half adiabatic. So you start with some ground state of some Hamiltonian, and then the last qubit here can be decoupled from the rest of the chain through a tuning mechanism. So this is the adiabatic decoupling that comes in. And then at the end, you can, once you decouple this qubit at the end, you can measure it. So you can just perform as you do in MBQC. But the interesting thing about the scheme is that the scheme doesn't depend on the specifics of the ground state. It only matters what is the symmetry of the system. So as long as you have the symmetry, you can do the computation. This is, he noticed that this is the idea of SPT phases, where the only thing matters about the phase is the symmetry. Next paper that I'm going to talk about is the one that was mentioned by Robert also at the beginning of the conference, is this Dominic Elsie paper from 2012. So this paper is interesting. So it's both like a step forward and a step backwards. It's step forward in the sense that now you're talking about proper MBQC. So there is no adiabatic part. But from the physics point of view or the computational point of view, this is actually weaker, because now you can't do computation, you can only do teleportation. The technical result is that you can do the computation throughout the phase, which was talked about by David also in his talk. So in 1D SPT phases, you can perform the computation throughout the phase, not just a fixed point in the phase. Technically, this is important because this imported the framework of group cohomology from the SPT classification. So SPTs are classified by group cohomology, but that technique was brought to quantum information through this paper. and we still use this formalism most of the time. And why this works is, okay, I'm not going to be able to explain the whole paper, but the typical kind of explanation of why the wire works in the whole phase is that if you write your MPS tensors, which represents the typical state in the phase, and then project it onto the symmetric basis, then this decouples into a logical subspace and a Young subspace, and you can use the logical subspace to actually compute. So you just use this subspace, well, not to compute but to teleport. So you can just use this subspace to teleport. So you measure in the symmetry respecting basis, and that simulates quantum wire. So that's where the symmetry plays a role. But the interesting thing is that if you actually want to do any computation that is not the identity, then you need to actually break the symmetry. So the resource states you start with, they are always symmetry respecting, but if you restrict yourself to measurements that only respect the symmetry, the only thing you can do is to teleport, nothing else. And but so you have to break the symmetry in some ways, but as soon as you break the symmetry, it turns out that that actually introduces logical decoherence in the system. And this is because now they don't decouple. So there is now these systems, there is some entanglement between them. So you can't just write them as tensor products. It's sum of tensor products now. It turns out this problem can be overcome, and the crucial observation that we make in this context is that the logical decoherence is to leading order not proportional to beta but beta squared. So there is no logical decoherence in the beta scale. So there is no logical decoherence in beta. And then, okay, so how you can use this fact is to employ a divide and conquer scheme, where you now split this rotation angle into smaller parts and then distribute it over different sites. And why this works is, okay, because they are far apart. Let's say they're so far apart that this is much larger than the typical correlational length of the system. Then you can treat these rotations independently, and when you do that, the total decoherence at an individual site is proportional to beta over m squared, because the local rotation angle is that, and because they are independent, you can add them up. But when you do that, you see that there is this extra factor of m that comes in here, and if you increase, so effectively when you increase the splitting, you can reduce the decoherence. So you can make the decoherence as low as possible. And in this whole part, the total rotation angle still remains the same. The only thing I want to say is that in this formalism, so at a technical level, you always need this large separation between this non-trivial rotation sites for the formalism to apply. You can't apply this whole reasoning if this is small. And for a technical reason, well, technically this is because what this large separation does is basically take your Young system to a fixed point, and that doesn't happen if you don't have this large separation. So I'm going to talk about the technical results now. First of all, okay, the reason we can have this new results is because of this new formalism that we also came up with. And okay, so this is a formalism that was developed a couple of years ago. So in this formalism, we get away from the MPS picture, and we actually take a more operational point of view on things. And I'm not going to be able to explain the whole formalism, but I'll give you a sense of how it works. But okay, once you have this formalism, you can ask, does this formalism just reproduce the previous results, or can it actually give you something new? And the counter and the regime I'm going to talk about is kind of an example of the fact that this formalism is more powerful than the previous ones, in some sense. Okay, how does this formalism work? I'll give you an idea. So let's just consider for concreteness the cluster phase, and I'm doing the simplest computation I can. So I'm just doing one site rotation. So I'm just breaking the symmetry of the, so I'm measuring in a symmetry breaking basis, and the symmetry breaking is given by this angle beta at site k. And if you translate it towards the circuit model, this is effectively this circuit. So you start with the plus state and then perform a rotation, and then finally you measure. If you want to know, how I'm going to describe the evolution here is I'm going to define a bunch of logical operators, and then I'm trying to track how the expectation value of those logical operators change as I go into the circuit. So I'm going to define a logical X operator, logical Y operator, and logical Z operator. I'm not defining them here, they're defined. I don't want to go into the definitions, but the way that this works is okay. So if you take a plus state, do a RZ rotation, and then measure it, the expectation value of X will be cos beta. That's what you get as a result of the formalism. If it's Y, you get sin beta, but because you are not dealing with the exact resource state you want, like not the cluster state itself, but some point in the phase, you get this extra factor here. So this is the typical string order parameter that people talk about in context of SPT phases. This is 1 for the cluster point, so you get the typical cos beta sin beta, but if it's not 1, you get something else. So the expectation value of Y is reduced because you are not at the exact fixed point. And there is a block sphere explanation of that, where because you are not, so you start with the plus state, you want to be, by rotating you want to be here, but because it's not the exact cluster state, you get somewhere on this red line. That was single rotations now, but there is no concept of a length scale here because there is just one measurement. So you need at least 2 measurements to see a length scale dependence here. And you see this with this example. So I am now doing 2 rotations, so site k and site L, and then you can play the same game. So you can compute the expectation value of the logical X operator and the logical Y operator, and this is what you get. So it's cos square beta minus sin square beta times another string order parameter. This string order starts here and ends here. Expectation value Y is sin beta cos beta times these string orders here, the ones that I defined in the first slide. But the interesting thing now is I don't need this delta to be large. I can compute this parameter for any values of delta. So I don't need this large separation of delta. And I'm going to show that in a figure next. So now I'm plotting the dependence of some parameters with respect to delta. I can do this for arbitrary values of delta. So from the previous expression, if I expand it to leading order, what I get is that the logical rotation angle is independent of delta to leading order. That's one fact. And then I also, if I compute the loss in purity, I see that there is a dependence on delta. Okay, so let me describe what the dependence is here. So the dependence is, so if delta is large, then I'm in the uncorrelated regime. So because I did splitting by 2, I should get a factor of 1/2. That's what I get. But I still get a reduction in the decoherence metric even if delta is small. So I don't get such a reduction, but I get some reduction. So when I make these rotations dependent on each other, there is an effect. I am not so efficient because now these rotations affect each other, but there is still a reduction in the decoherence. Okay, that was about 2 splittings. This is the general result for all arbitrary number of splittings. So we have arbitrary delta and then arbitrary number of splittings. It turns out that for that kind of setting, you can derive this universal scaling law. So the total decoherence metric is again beta squared over m. That's what we want with this prefactor kappa. And this prefactor kappa, this kind of absorbs all the dependence on this separation delta. And it's given by, okay, it's a little bit of a technical expression. Okay, let me say a little bit about. So the dependence of kappa on delta is given by this function f. Now I need to define what this function is. Okay, it's a little bit overload of definitions maybe, but this, you can think of this f as, okay, it only depends on the string order parameters. So once you know the string order parameters of the state, you can compute it, and you can think of it as capturing the strength of the correlations. So it's this typical condensed matter type expectation values of OI times OJ minus this decoupled expectation value. If you draw the typical graph of this function in the uncorrelated regime, it goes to 0. So then this term doesn't exist and you just get 1. But if it's correlated, you will get something, and then so you can see that this sum here is basically the integral under this curve, well, in some limit, continuous limit. Okay, but the upshot of this whole theorem is that MBQC still works in this correlated regime, because you can still, I mean, as long as kappa is as long as this is bounded, you can always reduce the decoherence arbitrarily by increasing m. But maybe you ask, okay, but what's the point? Like, why should I go into this regime? I mean, it's a technical result that you can do this for arbitrary delta, but like, what is the benefit I get by actually going into this dependence? That's where theorem 2 comes in. It says for MBQC on any state in the phase, the densest packing of the measurements is the most efficient. So this says that if you have a fixed length of a chain, so you have a constant number of qubits that you can use for the computation, then the best strategy for performing a rotation is to make delta as small as possible. And okay, I'm not going to give you a proof of this theorem, but I mean, there's two effects going on here. One is, so you have the number of splittings is m, and then there's a distance between them is delta. So as you split more, because there's this beta squared over m dependence, you get reduce the decoherence. But if you if you increase m, because you only have a constant number of qubits, your delta decreases. But that will also increase the decoherence because of this dependence on each other, and there is an interplay between those two. And I mean, at the end, it turns out that when delta is the smallest, that is how you optimize the decoherence method. That's kind of, I don't want to go into the proof of that, but this is kind of the final result that you get. So you actually gain by going into this weird regime. Okay, so maybe this is a numerical confirmation of the result. So I'm considering some ground state of this Hamiltonian, and I'm going into some, looking into some resource state, and I have a constant number of qubits, and then there is the decoherence metric here, and then there's dependence on delta. Any deviation from this line means that you are going into the correlated regime. So anything here, these are uncorrelated, but now this is correlated, and you see, as you go into lower and lower delta, you are moving away from this line. So you would be more efficient if you were in this line, but you can't do that. But you still gain by doing this reduction. So if you just stayed here, you are not as, your decoherence metric is not as little as if you are here. So now that we can handle kind of strong correlations, maybe we can handle also genuine topological order. And this was actually done by Paul, and that's probably the next talk. Not going to talk too much about that. Okay, now this is the general question: is can we find the most efficient MBQC scheme for arbitrary phases and arbitrary unitaries? So I did this for the cluster phase and just rotations about a particular axis, but can this be done for arbitrary MBQC in these phases? And this is something I'm working on with Lucas about these geodesics and subdominion manifolds. And then there is the big question about what is the this is not just this talk, but in this whole area, the big question about what is the physical counterpart of MBQC computational power in this context. Okay, I end with a take-home message. Yeah, don't fear strong correlations, embrace them.